Alright, so these are the problems that you were supposed to go home and complete. So let's go ahead and just jump right in and look at the answers to these. Alright, well, as soon as it pulls up here, let's try again. There we go. Alright, so it's been a morning of technical difficulties so far, so maybe we'll get something here. Oh, maybe. Oh, here we go. Maybe we'll get there. All right, let's get this guy out of the way. Okay. Here we go. Let's see if this will work this time. There we go. Okay. All right. So once again, we're doing the integration piece here. This may be a lot more helpful if you rewrite the problem. Alright, so that's what I'm going to do first here, is write these as a power rule problem. So this is 3 and then x to the negative 1/2 minus 5 x to the 1/2 minus x to the negative 3/2. So once again, for some of you, writing it as a direct power rule problem would be more beneficial. Now, when we do the antiderivative, remember your notation. Alright, so we're going to put this in brackets. So I add a power, so I'm now to the 1/2 power. I divide by that power, so dividing by 1/2 same as multiplying by 2. Here I add 1, so I go from the 1/2 power to the 3/2 power. And then I divide by 3/2, same thing as multiplying by 2/3, so I end up with negative 10/3. Here I add a power, and I'm to the negative 1/2 power. Divided by negative 1/2 is the same as multiplying by negative 2, so this becomes a positive 2, and then we are integrating from 1 to 4. And then once again, now we evaluate all of this at 4, so 6, alright, times 4 to the 1/2. Minus 10/3, 4 to the 3/2, plus 2, and then 4 to the negative 1/2, and then minus, I'm going to write that all below right here, and this is just going to be 6 minus 10/3 plus 2, since it's all 1, and then you would just go through and calculate all of that and get your answer. Alright, so let's move on to the next one. Once again, this is basic trig rule. Alright, the antiderivative to cosine x is just sine x, and so that's my antiderivative, and we're going to evaluate that, alright, at these two values. Alright, so sine of pi over 4 is radical 2 over 2, and then I'm subtracting, and the sine of negative pi over 4, now remember that is in our fourth quadrant. Sine is negative in the fourth quadrant, so it becomes a positive radical 2 over 2, so that is just radical 2. Alright, so let's move on and look at another example here. Alright, so now as we look at this guy, alright, so once again, I mentioned this in class, that really we're really doing our two main rules. It's basic power rule, or it is basic trig rule. If it's not one of those right now, really it's kind of a rewrite rule. Alright, so at this case, when we look at this, this is a basic rule. This isn't quite a basic rule. Alright, so we just need to rewrite this, and I'll just rewrite it right here. So we're going to go from pi over 6 to pi over 2. We still have our x here. We have plus 2. And then another way I can write 1 over sine squared, alright, would be cosecant squared x, like this. Alright, and then what we should know is that cosecant squared is the derivative of one of our rules. Alright, so then once again we go through this. This is going to be x squared divided by 2, because this is power rule. And then the antiderivative cosecant squared is negative cotangent, so this would be negative 2 cotangent x, and then once again we're evaluating, and then our lower limit is pi over 6, and we're at pi over 2 here. Alright, so now we go through this. So we have 1/2 times pi over 2 squared minus 2, and then cotangent of pi over 2. Let's see, so that would be cosine of pi over 2, which is 0, divided by sine, which is 1, so that's going to be 0. So there's our first. Minus, now we plug in pi over 6. So we have the 1/2, and then we have pi over 6 squared minus 2, and then we're going to have cosine of pi over 6 over sine of pi over 6, and then you would evaluate all of that and get to your answer. Alright, so hopefully this is making sense to you. You're seeing how we're combining the two previous ideas that we were using, and then once again this is finding that exact area under the curve. Alright, so now a couple of applications, alright, from our definite integrals. Okay, so one thing that we can do now is find an average value of an entire function. All right, so now what I would like you to do is maybe pause the video right now and go ahead and write this formula down. All right, so to find the average value of a function, all right, you basically take the integral from a to b of f of x dx, just like we're doing, and you're going to multiply by 1 over b minus a. And that is like adding every possible value we get from a function and dividing by an infinite amount of those values. And I'm going to go through a derivation of this formula for you. Not that you will have to reproduce that or do that. All right, you'll just have to be able to use the formula. But I want you to see where it comes from, a couple of big ideas that you should know from this course and from some other work that you've done in mathematics. So, all right, so if we look at this, all right, let me pull the screen shade up here. Maybe? No? All right, that way maybe you don't get overwhelmed with all of the work here. Okay, so the first thing that you guys probably know is that when we're finding the average value of something, we add everything up and we divide by the number of those things. So if we're thinking about a function, I would add up every function value, all right, that I had, and I would divide by the number of those function values, and that's the notation that you see here. Now, what we can do then is simplify this notation using summation notation. All right, so I still have the 1 over n, which is this guy, which is the number of function values we're adding, and then I'm summing those all up to n. Now, once we get to this point, all right, what we're going to do now is just do a little bit of algebraic manipulation, all right, to get it to an integral. So the first thing I'm going to do is multiply by this b minus a over b minus a. So notice this is just a specific one that I'm multiplying by. All right, so we went from this step to this step just by multiplying by a special 1. And then now it becomes a little bit more manipulation. Let me once again go through this so you can kind of see it step by step. So there's that guy, multiplied by a specific 1. Now we're just going to do a little bit of trading here. All right, so we know b minus a is a constant, so I can pull it out front, which is what I did here. This is also a constant, but I can pull it back in, so I get to this guy, which is b minus a over n. Now, if you recognize that from all the work that we've done, that b minus a over n is equivalent to delta x. So now, if you see, we have this 1 over b minus a out front. We have the sum from I equals 1 to n of f of c I delta x. And we know, all right, that this is how we get to our definite integral. All right? And so then if we apply the limit, because we don't want to just add a finite amount, we want to add an infinite amount, all right, we end up with this limit as n goes to infinity, and we know that this turns into our definite integral. All right, and so then that's how we get to the formula, all right, that you saw on the prior pages. All right, so that's how we get to this guy right here. All right, so we know the limit gives us this piece, and that 1 over b minus a stays out front, and that's what you see right here. All right, so let's just go through an example here. All right, so we want to find the average value of the function. All right, so all we have to do, the average value of f is equal to 1 over b minus a. So b minus a in this case would be 6. And then we take the integral from a to b of whatever function we are working with. All right, so this is 1 over 6. Now we do our antiderivative. This would be x cubed over 3 minus x squared from 0 to 6. All right, we have the 1 over 6 out front. All right, and so if I plug 6 in here, I get 6 cubed divided by 3 minus 36. And then if I plug 0 in, this is all 0. All right, so then if we look at this, 1 over 6 times this would leave us 36 over 3 minus 6. So that's 12 minus 6, which is equal to 6. So the average value of this function is 6. Now, this is adding every value from 0 to 6 that it would be on this curve. So everything but every point you could possibly plot of x squared minus 2x from 0 to 6, and then averaging those, dividing by that number, and that's what this 6 represents. Okay, now, another extension to this is, all right, if you look, we have this average value right here. Now, this is called the mean value theorem for definite integrals. Now, it should make sense to you that if this is the average value, all right, then there should exist one point on the curve equal to that average value if our function is continuous. So we have no breaks, no jumps, no gaps, nothing like that. All right, so this works if we have a continuous function. All right, so if this is the average value, all right, then this, all right, exists somewhere on the curve. Now, if we multiply by b minus a, let's talk about what this, all right, represents geometrically. Now, we know this is, all right, the exact area under the curve. Now, f of c is a height, b minus a is a width. So geometrically, what this is telling us, if this is the exact area, under the curve, we should be able to find at least one rectangle, all right, between our minimum rectangle, that smallest rectangle we've talked about, and that largest rectangle that we've talked about, that is actually equal to the average value. All right, so when you work with this this type of problem, you can think of it in one of two ways. You can go ahead and just multiply it this way, or you can do it this way, so whichever way is your preference. All right, so let's talk about a couple of these problems. All right, so we want to find the values of C guaranteed by the mean value theorem. All right, so let me pull this up here. All right, so when we look at this, all right, so what we know is that there has to exist some value that's equal to the average value. All right, so if we just write this guy in like this, right? So that's our statement. So f of c would be if I plug c in here. So that would be c cubed. And we have 1 over b minus a, so we're going from 2 to 3, so that's just 1. And then we're going from 2 to 3, and we have x cubed dx here. So then if I integrate this, c cubed would equal 2, and then our antiderivative would be x to the 4th over 4 from 2 to 3. So then c cubed would equal to 3 to the 4th. So what's that? 3, 9, 27, 81 fourths minus 2 to the 4th. So 2, 4, 8, 16 divided by 4 would be 16. All right. So then I get c cubed is equal to, and what is 16 fourths? Is that 64 over 4? So we'd have 81 fourths minus 64 fourths. So what is that? 16, 17 fourths? And then I would take the cube root of this. So c would equal to the cube root of 17 fourths. So now this value, all right, should be somewhere between 2 and 3. So a good way to double check that, all right, when you do your work. All right, so that's kind of how you find, all right, that mean value theorem, all right, that value. So what this is saying is that the cube root of 17 fourths, that is where we take on that average value. Okay, that is where we could draw the rectangle. All right, that would be equal to the exact area under the curve. All right, so a couple different ways of thinking about that type of problem. All right, now let me go ahead and pull up a clean screen here, and then we'll look at the next one here. All right, and so once again, and I'm just going to do this right here, but we're going to work with this problem. All right, we have our f of c would equal to 1 over b minus a from a to b of f of x dx. All right, so now f of c, and then once again I would go ahead and multiply this out, so we would look at it as a polynomial, as versus a product of polynomials, just to make things a little bit easier. So if I do f of c, that would be c plus c to the 4th equals, all right, and then I do 1 over b minus a, so that's going to be 3, so this is 1/3, since we're going from -1 to 2, and then we're going to go from -1 to 2, and then this would be x plus x to the 4th dx. I should use parentheses there instead of brackets. All right, and then once again, you just go through the process here. So 1/3, we do our antiderivative. Okay, so x squared over 2 plus x to the 5th over 5. We're going from -1 to 2. So c plus c to the 4th equals 1/3. So we plug 2 in. 2 squared is 4, divided by 2 is 2. And then 2, 4, 8, 16, and then we have 32 fifths there. Plug in -1, so then that's going to be 1/2 minus 1/5. All right, so we get 1/3 here. All right, so let's see what we have here. So 2 minus 1/2 would be 3/2, and then 32 fifths minus a -5th would end up being 33 fifths. And we multiply by 1/3. All right, so that's going to end up being 1/2 plus 11 fifths. All right, and so then that would be what that's going to be. Let's get to tenths, I guess. So 5 tenths plus 22 tenths. So what is that? 27 tenths. All right. So now, when you look at this, not an easy thing to solve for C here. So I wanted to also make sure, and why I went through this problem with you, you may have to go ahead and graph this. All right, so you might have to put in like x plus x to the fourth, and as your y1, put in 27/10 as y2, and then use the intersection feature on your graphing calculator in order to find that value. All right, so as you progress through the homework, if you get to something like this, that doesn't look like a typical type of algebra problem, so not like factoring or something that you should be able to solve very easily, know that you may use your graphing calculator for some of these types of problems. All right, so just one more type of problem, and then we'll wrap things up. All right, so integrals and total area. All right, so now what we have to make sure is we read the question. All right, so anytime we're just looking for the value of an integral, all right, it is the net result. All right, but anytime it asks us to find the total area, okay, what we have to do is find, okay, where does it go below the axis, the x-axis? Where does it go above the x-axis? All right, and we have to look at all those individual integrals individually to find those each area, and then add those together to get the total area that we want. All right, so when you do this, all right, you want to find the zeros of the function that you're integrating. So once again, if this is a function that is very easy to solve, you know, quadratic, a simple polynomial that you might be able to factor and get your zeros, great. If not, okay, you may have to graph it first, find those zeros, okay, use your calculators. All right, and so once you do that, what you want to do is create an interval for your integrals, all right, between these zeros, between your x-intercepts over the interval that you're integrating. All right, so now once you do this, all right, you can integrate each piece individually, all right, and then just take the absolute value of those pieces and add them up. All right, so let's look at a particular problem here. So something like this. All right, so when you look at this, all right, we want to find the total area. All right, and I'm going from -1 to 8. So what I want is a positive result at the end. So once again, when I look at this, all right, may not have been a great guy, all right, to solve algebraically. All right, so I graphed it here and give us a picture so we can see from -1 to 0. All right, I am below the x-axis, so that would be one integral. So I would take -1 to 0, and I would integrate this function, so the cube root of x minus x dx. And then I can see, okay, from 0 to 1 is positive. All right, so then I would create a second integral, 0 to 1, x cubed minus x dx, and that would be my next integral. And I can see that everything from here to 8 is below the axis. All right, and then so that would be my final. Let me put that one a little bit lower there. All right, that would be my final integral right here, like so. Now, you can do this a couple different ways. So you can just go ahead and calculate this and then know, okay, I can take the absolute value. If you want to put the absolute value bars in, all right, like this to start the problem, that's fine too. All right, sometimes the absolute value bars bother people. They seem a little bit cumbersome as far as carrying things through. So I'm not a real big fan of using the absolute values in my problem. So typically what I will do is I will go through a problem, and then I know that, okay, I just need to make it, I think this was -1 here, okay, we got 0 here, and we have 1 here, and I just make them positive at the end. So if I were doing this particular problem, I'd say, okay, the antiderivative, okay, this is x to the 1/3, I'm going to add 1 so I get to the 4/3, all right, so then divide by 4/3 is 3/4, so then minus x squared over 2, all right, and we're going from -1 to 0. So I plug in 0, okay, I get 0 minus 0, great. Plug in -1, I get negative, oh no, it's basically become a positive 3/4 minus 1/2. All right, so 3/4 minus 2/4 is 1/4, so that's -1/4. So then I know, oh, this is really positive 1/4 for that area. All right, and if you did that, that also ended up being positive 1/4. It is symmetric right there. And then I just kind of change it at the end versus putting the absolute value bars in to begin. All right, so that's where I'm going to end and wrap this up for today. All right, so once again, just go ahead and I'll just pull up the homework here. So you should be able to go through and complete this entire assignment. All right, so once again, remember that you are going to be doing your antiderivative, so look for your 3 basic steps here. Is it basic power rule? Is it basic trig rule? And if it's not one of those 2 guys, then just go ahead and rewrite, okay, so that it is. All right, so that could be an algebraic manipulation, that could be a trig identity, all right, rewriting it as another trig function, those types of things. So that wraps up our lesson for today, all right, and then you guys have a good weekend. I will see you Monday.